Probably I'm gonna do 5 to 7:15. Give you guys 15 minutes, like the midterm for like submitting. Is it good?
Yes.
No, I unfortunately I cannot do earlier because that's the exact same time of the class, so I cannot do earlier. So unfortunately, that's the exam day, so I could not change something for that. So that's need to make sure just join online, submit online, so everything gonna be in the good shape. So that's a final exam. And what
Can you
else
give
I'm
the
gonna
time one more time, please? Sorry.
the final exam is on June 30th, which is gonna be this Friday. It's gonna be from 5 to 7:15. I put
Okay.
like the midterm 15 minutes for submitting everything. Just please figure it out if you wanna need it, your laptop, Gmail, anything you need to submit it. Just make sure everything is gonna be in the best shape.
How many
before
questions on the final exam?
I don't decide it yet, so I didn't know write it yet. Whenever explain about like the recording that you are gonna see in Canvas, that I'm gonna explain how many questions gonna be in the final.
On the one
Probably
that's
5.
specifically for the study guide?
Yes, that's the first study guide. Yeah, I will explain a few things there, sure.
Ah,
And then I will post it on Wednesday morning. So Wednesday like 11, something like that. You guys can look at it. And then if you guys have any question about the topic, the 2 classes that I'm teaching on that time, you can ask me on Wednesday or Thursday to make sure you guys understand everything. Does it make sense?
okay. Can you just do like an announcement for like important pointers like we spoke about like in the last 10 minutes just for us to like go back?
Oh, you mean? Okay, I will send an announcement. Sure.
Yeah.
I will send an announcement about final exam, 2 recording class, and then and the TA is grading. So
can I get the email for the TA so I can send him the quiz 8?
I think you can search his name in Canvas. His name is Harsh, so you can find it probably.
Harsh?
So I want to say yes.
Oh.
Okay. Let me check it out. So yeah, I introduced him actually in the Canvas. You can find it in announcement, but did you find him? So this is his email.
I'm looking for him right now.
I sent the email here. His name. Okay, with his email. So I send it to everyone. So you're welcome. I will send an announcement in about these 2 things, 2 recording. One more thing. I'm gonna post the I think probably I'm gonna post it tonight or tomorrow. I'm gonna post another additional homework 3, which is gonna be only 3 questions, and it's gonna be extra point if anybody wanna solve it by Friday. It's not mandatory, but just in case if you want to get extra points.
I have another question. I was wondering about are you gonna fix the weights for the quizzes? Like on like you know how you said at the beginning of the semester is 10% for like attendance and quizzes? I was wondering.
No, first of all, I need to see what is the grade for midterm. So we are grading the midterm, so let's see how is the grade for midterm first.
Because honestly, quiz 5 really destroyed me. Like, didn't have time on it. Like, it's kind of screwed us, most of us, over. You know?
Yeah, 10. I cannot go less than 10%. I'm trying. Probably I will go more than like 10, or I'm not gonna decrease less. It's not gonna be less than.
Can you remove quiz 5? Because that
no,
one,
I cannot.
that's the
I'm
one.
So sorry.
Are you gonna, Professor? Are you gonna be dropping any of the quizzes?
No, I'm not gonna drop anything. So I just give you guys example before you know what's going to be in the quiz probably. That's the 10% is not that much. If we need to just have like solve the problem. So the only thing I just trying to just do, I'm gonna give extra point for 1 homework if you want to submit it. So if you want to compensate whatever you lost in the quizzes or midterm or final exam, or you can just submit the homework 3.
Okay, so I'm confused. Are you gonna change the scaling of the quiz grades then?
No.
Because right now they're more than 10%, and you said they were gonna be 10%.
I look at the I think I probably go whatever I just started from the beginning of the class. Whatever I just mentioned, that's gonna be. I'm not gonna change it.
Yeah. So I think basically the Canvas grades are not correct then, right?
No, it's not, because there is no weight there. It's not
Okay.
correct.
Is there
no
any
weight.
way we can like actually not?
We need to wait because all of the quizzes should be in the same structure. So at the end of the exam, so I can put weight on all of them, so it can calculate it by itself. But you can calculate by yourself by hand too.
Yeah, if you have to calculate your grade, you can use a grade calculator, and the weights are on the syllabus.
Yeah, you can calculate that. And the only things about homework 3, if you want to submit this one, like that's optional homework. Just that's happened in the previous semester. Don't copy paste. Don't cheat on the last additional homework. That's happened previous quarter, like semester. So people cheating on the additional homework that has they're trying to compensate something, but they're just cheating on it, and then they destroy the grade. So just want to make sure that you guys understand. That's the additional. If you want to submit it, just go ahead and submit it. That's going to be the additional point. But if you don't want to submit it, that's okay too.
Wait, when is the additional homework gonna come? Sorry, I can't really hear. My mic's kind of.
So we have another homework 3. I'm gonna submit it tomorrow morning. This is only 3 questions. So if you wanna solve it, and then you have deadline until Friday evening after the final exam to just go ahead and submit it. That's gonna be extra fun.
All right, thank you.
If anybody, yeah, you're welcome. I just want to help you guys. So if anybody wants to compensate whatever happens in the quiz, midterm, or final, that's the only way that you guys can just do it.
Okay.
Thank you, Professor.
You're welcome. So it's not done yet, the midterm grade. I cannot say how is it because I need to have all of the students to see, but we are finishing. You see that we're finishing like quizzes, and then we only have quiz, I think 5, 6, let's see. The grade quiz 5, there is midterm and quiz 6, 7. And yes, we are finishing all of these things by, I don't know, Thursday. So, or before Thursday. Let's see how it works. Yeah, I'm trying to help. I cannot pass you all, you guys. I don't know what you're asking. That's interesting. Okay, anyway. Okay, I know that's a really short semester, so probably that's too many things to learn at this, I don't know, 1 month and a half, maybe it's less than 1 month and a half, but that's one of the things I'm trying to just help you guys. No, you cannot get A being a good student, probably. Okay, so let's start getting back to whatever I was teaching the other day. So we were talking, the last point that I was talking about, it was minimum weight spanning trees. Let me start sharing my screen and then let's go back and try. Okay, so let's see. It's lecture 17. So. It's one more thing. We grade everything up to quiz, I think 6, and the homework. If you have any question about any of the quiz or anything is missing, just send me an email and CCTA. So we probably know what's going on. Don't wait to the last minute. Does it make sense?
Yeah.
Don't reach out to me after the exam, everything. So go, I have some issue like this, and it's gonna be really late. If you have anything you need to tell me or any issue, just it's a good time to start reaching out to me. But after the exam and everything, I'm just gonna grade everything. I'm gonna post the final grade. I cannot change anything if I post the grade. That's all. One of the things I want to mention. Make sure that you guys understand. Okay. So let's see. Now we are talking about the spanning tree. So that was the last thing that I teach. Then I say there are 2 algorithms that we can talk about when we are trying to work on a spanning tree. You remember what it was a spanning tree. So that was what we are trying to do, minimum spanning tree. We say, okay, it's a tree that we are trying to find the minimum. We are trying to say, okay, this is a tree. We are trying to connect the tree as a graph that is connected. There is no cycle and the weight is minimum. So that's what's the definition of minimum spanning tree. So we talk about how is the weight and how we can define how to find trees. And there are two algorithms actually. So I know probably when you have an example, so you want to know how to find this minimum spanning tree. There was two algorithms I was talking about actually. One of them was like primes, and then there's Kruskal algorithm. Let's talk about that one first. So let's go ahead and then talk about the algorithms here. So let's see. So first of all, when you're trying to solve this problem, what you need to do, you need to choose an edge of minimum weight, because you want to find a tree which is it's a connected tree which doesn't have any cycle, but the weight is minimum. So what is the best approach? You choose an edge of minimum weight. So that's the first step. I think that's obvious that you choose one of them that has the minimum weight. And then whatever you are gonna do amongst all edges, whose addition would not create a cycle with previously chosen edges, chose one of minimum weight. What does that mean? I start with one edge, which is the minimum, and then you look at among all other edges, if you add them, it doesn't create a cycle, and then it has a minimum weight. So if there is 2 or 3 that doesn't have a cycle, I chose the one that has a minimum weight. So that's what I'm gonna do after that. So, and then I will add everything, stop. We will do one. First we start with one, add, and then go ahead, and the next one, stop when n-1 edges have been chosen. Why I'm talking about this one? Because as you remember, when I was talking about trees, I say, okay, if I have n vertices, n-1 edges needed that we make sure we have a tree. We have the connected tree. So that's the reason we need to keep going until we have n- edges. That's the first thing we need to do. So does it make sense? So let's go back and talk about some of the things. We talk about this one. We say, okay, G is a tree. If G is connected, and then the number of edges is equal to number of the vertices -1, and then, or is it there is no cycle, and then the number of edges is equal to number of the vertices -1. So that's the definition of all of these things that we talk about that one. So what's going to happen? Let's go back here. So I guess, okay, this algorithm, how it does is, okay, the number of the n actually is the number of the vertices, and m is the number of the edges. So we choose an edges, first to start the edges of the minimum weight, while all the edges is chosen is going to be less than n-1, because among all the edges. Among these all edges, we need to create sockets. Here, what we do all the time, say while number of edges chosen is less than n-1. That's what's good. You need to keep going, adding until it's less than n-1. You should not go over that, because if you go over that, it means that it's not going to be a tree. So you will do this one. You chose the one doesn't create cycle and it's gonna be meaning. So we do this one. So some of the remarks that you need to never forget when you do these things. First is that at each stage, the chosen edges from an side spanning subgraph of G. It means that each edges that chosen edges from an cyclic spanning subproblem of G. So it means that every time you're solving another problem, you're just doing subproblem spanning of G, spanning, which you name it as a spanning forest. And one more thing you need to mention, when the forest contains n-1 edges, it must be connected. Because if it's not connected, it means there is no tree. Seeing any cyclic graph on n vertices and n- edges is connected. That's a definition that we have actually for like any, like the forest. That's a forest that have n- edges. It must be connected because all of these edges needs to be connected. Other than that, it's not going to be a tree. So connected by tree nesting. It means you make a tree. So it means what's going to happen. So this algorithm, what's gonna do, builds a spanning tree called it T. It means in each step, it's gonna create another spanning tree, call it T. So first of all, so what we did, we just, okay, each step we choosing from edges that doesn't make it cycle, which is going to be another spanning forest. And this is spanning, we need to have at least n- edges, and then they should be connected because it's like there is no cycle between them. So it's like a tree, another tree. And then so we build a spanning tree on that. So let's talk about a theorem that to solve these things. Let's go back to one of the theorem talking about this. Is it clear? So it means you generate so many spanning tree, and this spanning tree we generate has minimum weight. So we say, okay, this tree T that we built by this algorithm it's a spanning tree, but has minimum weight among us all spanning trees in G. So it means if in G you find so many spanning trees, this one that we consider that just we use this one each time you first start with the minimum, add one, it doesn't make cycle, it's minimum. So that's gonna be at the end of the day, this tree has a minimum spanning tree because at each layer, so you're choosing the one has a minimum weight. So let's talk about how we prove this one actually. Let's see, why do you see this is gonna be the one that I'm building is gonna be the minimum weight. We can let S be any other a spanning tree in G. What we need to show, we must show so this tree that we have, if this is a minimal spanning tree, this weight of this tree is going to be less than weight of any other spanning tree that we have. It doesn't matter. Anything, it should be less because we know that this T is going to be minimum. So we say, okay, let ET, this is the number of edges. So let's see, okay, this is the edge E1 up to E minus 1. We know why it's up to E minus 1 because as we explained earlier, for making a spanning tree, if we have n vertices, we need to have n minus 1 edges. So that's the reason it starts from 1 and go all the way to n minus 1. And so it's given in the order chosen by Kruskal algorithm. So it means any of these edges as I start from 1 to n minus 1, any of them, when you chose them based on the, okay, is it minimum, is it not making a cycle, and is it minimum? So we do it one by one, adding one by one. So if that's the case, since we know that S is not equal to T, we know this is not equal at the beginning. So, okay, we know this is not equal. So if it's not the case, it means there is a first edge, like EK, there is one edge in T which is not in S. That's the case because if they are not equal and if they are like a spanning tree, it means that there is one edge which is gonna be EK. It is gonna be in T, which is not in S because they are not equal. So it means that there is one. So if that's the case, we say E like this one. It's okay. Anything that start from E1 up to EK minus 1 is in edge of S. All of them is in edge of S. The only thing means EK is not. It means we go all the way up, and then we realize, okay, all the way up to here, we just make a tree. We just add everything. It doesn't make any cycle, and then the weight is minimum. But at one point, we realize we chose another edges. So it means that edge is not in, it's in T, but it's not in ES. And so what's going to happen? Then let H be the subgraph obtained by adding EK to S. So find another H, which is gonna be like another subgraph, and just what you have, you know that S doesn't have EK. So let's add it to S. So H is gonna be another graph which has S, not only S, it has EK too. So based on by treeness theorem is definition of tree. You remember I explained, okay, what this is gonna be tree if this is got 3 cases. By treeness theorem, H contains a unique cycle which contains EK. Call the cycle. Why? Because as we know, S by itself is not, it doesn't have a cycle. It doesn't have a cycle, and it's a tree. If we have n vertices, we need to have only n minus 1 edges. If this n become n, it means it's not 3 anymore. So it means it's 3, but there is a cycle. So that's going to be, because you add one more edges, you make a cycle out of that. So contains a unique cycle, but probably because we add one more edges, so we are going to have a cycle. We call this cycle to be C, actually. So, and then notes what's going to happen. Node C must contain an edge E of S that is not in T. So why we say this one? We say, okay, because we close the cycle and now we have this node that C and it has E, one of the edges of S. So it means if it's in S, but it's not in T. Why it's the case? Because if it was otherwise, T would contain C. But T is not, it doesn't have cycle. So C, since it doesn't have a cycle, it means that this E is only existing in S and it's not existing in T. So now what we are gonna do, now remove this edge, E from edge. So what's going to happen, and call resulting subgraph. So if I start by removing this one from all the edges, now I have another graph which has H minus E, which is going to be S plus EK minus E. So now that's a definition because H was S plus EK. So now that's going to know now that nodes R is connected since we remove a cycle edge. If we remove the cycle edge, they're still connected because we remove only the cycle. We didn't remove anything else. We just remove the cycle. Also, R has n minus edges. So must be a spanning tree. So now if R is it doesn't have any cycle, R has n minus edges, so it must be a spanning tree too, because not only it doesn't have cycle, it has n minus edges, so it's going to be another spanning tree. So the nature of the Kruskal algorithm, that because we say everything we added after that, it means it has more weight. So that's going to show that the weight of the EK is going to be less than the weight of E, because we are going to add this one. Anything after that, every time you add one edges, that new edge has the more weight than the previous edge, because we knew that, because the new edge is going to be greater every time we chose the minimum. So that's the case. So we say, okay, that if that's the case and E does not form a cycle with EI and up to A kind of EK minus 1, since we know that all the E1 to all EK minus all the way to E, all of them is in. Let me write it better. So why we say since E1 all the way to EK minus 1 and then E is gonna be in the subset of the E of S, because all of these things is gonna be subset of E of S. So we say if V of E is less than V of EK, then Kruskal would have chosen E on k's iteration. Why? Because we say that if we say that WE, which is going to be the weight of E, is less than EK, it means we chose E earlier because we chose it earlier. If it's not the case, we cannot have this one less. So instead of EK, which is the contradictory, it means it's not the case. So we say W of EK is less than W of E. That's the thing. We cannot do other than that, because if that was the case, we chose it in another way. So if that's the case, we say therefore if that's the case, we say therefore W of R is less than equal to W of S. Because we know that one, because we removed that one, we know that we chose E of K earlier, so that's going to be less than that. So also R has one more edges in common with T. Because there is one edges in R, it has R, which is going to be common with T than S. Because if there is it's not in S, but it's in T, so S does. So what's going to happen? So we say, okay, E of S, all the edges of S is going to be E1. We say all the way to AK minus 1, and then we have LK, and then go all the way to. So we talk about this one. This part is in T. This part was different than T, not in T. We explain this one. And then let's go back to the E of R, edges of R. So we say, okay, edges of R, E1 to E2, all to K minus 1. Is it gonna be L? And then this is gonna be, this is exact same thing. This is in T. And this one is in T too, because it's not in S, but it's in T. So that's the other thing. So we have that one. So what it shows, so probably it shows that because everything is quite similar, it shows that if R is equal to T based on the structure, we are done. Why? Because we say, let's start with this one. We say, okay, we want to prove that all this T that we have has the minimum spanning tree. So we start with any tree. We say, okay, every tree T is going to be less than WS for sure. And then we say, okay, if we remove that one, we can get to another R sub problem. And then we show, okay, if R is equal to T, so it means that we are done. We show that, okay, because here we show this one. We say W of R is less than W of S. We prove that one. If R is equal to T, we prove the problem from the beginning. So it's already done. But if it's not the case, if it's not equal, so we are not done. So okay, because everything here in ER is similar to T, all of this one and this one, we don't know if the next. So what we can do, if not, then we can do the same. Do the same construction. It means that we remove one edges, we do exact same thing with R, and then we see, oh, okay, this one has the better. So in place of S. It means you do, instead of this one, now let's go to sub problem. Instead of consider R to be S, and then you prove, okay, S gonna be this one. So what's going to happen? Then we construct a spanning tree R2 with one more edge in common with T. It means W of R2 is less than W of R. So that's going to happen. And then you go one layer down. And then if you continue this one, what's going to happen? Then continuing, we obtain a sequence. So what is going to be the sequence? We start with S, we build R, and then go to R2 all the way, then we realize we are reaching R. S. So this is going to be R0. It means probably that's going to be same structure. You consider R1 and they'll go all the way to T. So eventually what's going to happen, we must reach T. And then what we found? We have, because every time, let's see, every time we just remove one, the next one is going to be less than the previous one. So if we do S, go to R, R was less than S, R2 is less than R. And then if we reach to T, because we remove everything, that's going to happen. So W of T is going to be less than all the way all to W of R, which is less than. So, which is going to be, okay, let me write it better, actually. W of T is going to be less than equal to W of R2, which is going to be this one. And then this is less than W of R. And this is less than W of what? R0. R1 and R0. Which is in the structure that we have. R0 is R and R1 is R1, R1 is R, and then R0 is S. It means that if you go down all the way, we realize, okay, so W of T is less than W of S. So that's what's going to happen. We showed that W of T is less than equal to W of S. So you see, we show, okay, I'm just building a spanning tree, smaller, remove one. And so, okay, this is going to be less than, the weight is going to be less than, and then at the end, so, okay, T is going to be the last one. And then, so we show that the weight of the T is less than all the one before that. So does it make sense? Is it clear? Okay, sounds good. So we should prove that one actually. So that was one of the algorithms that we can show. There is another one which is named prime. Probably I'm gonna teach that one for the record. So when I'm recording. So, but now after all of these things, when we explain about a spanning tree, what is a spanning tree, how to find a minimum spanning tree, we need to go to the lower bounds. So instead of solving the problem, you're trying to find a lower bound, which is going to be runtime. So, okay, what is the lower bound for all of these problems? So we are trying to solve that one. That was the definition of lower bound. So I'm going to explain lower bound. So, and then we move forward with lower bound to see how much I can teach today. And then we are going to keep going by recording for tomorrow. So let's see. Let's go to lower bound actually. Okay, we say consider some problem P in all its instance to goal. It means what's going to happen as what, for example, I explained earlier. We go to sub-problem and instead of solving the problem, so consider some problem and all its instances. It means all of these instances that we have two goals. First, what's the goal? Find an algorithm that solves P. We just want to solve the problem that solve P and find an asymptotic upper bound for its runtime. So, okay, O of Fn. So our goal is to find an algorithm that solves P. Find a one that, for example, when a spanning tree, we are trying to find an algorithm that solves this problem. But the upper bound, what is the runtime? So it's going to be O of Fn for some function Fn. So what is our goal? Actually, we aim to reduce f of n by finding better algorithm. What does that mean? So you remember, for example, when we were talking about sorting algorithm. For example, what we did, our goal was to solve the problem. We want to sort the array or anything you want, but we felt, okay, let's find a asymptotic upper bound for that. But remember, for example, we solved one two loop algorithm. We realized, okay, the upper bound is O of n squared, because we just go through all the layers one by one, and then f of n is going to be n squared. So we find it. But you remember, we go to merge sort. Why? Because we are trying to realize, okay, there is an algorithm which do the sorting with n log n, which is going to be the better algorithm because it reduced the runtime. So that's all the problem that we are trying to do. So if you have a problem, you're trying to solve it in different ways and find the one that has a lower, actually has a better runtime. So does it make sense? Does it make sense? Okay. That was the first goal. It's understandable. You're trying to find the algorithm to solve the problem. Like, if you want to consider time, you're trying to solve it faster. So it's okay, find this algorithm. First, the algorithm that solves the problem overall. Find the runtime and find the one that do a better job. So what we are going to do, prove that any algorithm solving P runs in time. Like if we find any algorithm runtime is going to be big omega of g of n, which is got a lower bound for some function g of n. We aim to increase g of n by decreasing better proof. What does that mean? So we are trying to prove that any algorithm that solves this one runs in time of lower bound of omega gn for function. We aim to increase g of n. It means that lower bound is going to get higher and higher. It means that the proof that increase by decreasing better proof. It means that you're trying to increase g of n by decreasing the better proof. So what does that mean? So it means that we are going to reach to this one. So, okay, what you are trying to do? Let's see. You're trying to increase, like you're trying to decrease O of n, increase omega n, for example, like f, okay, f of n. And then you are going to reach the point that these two is going to be equal to each other. It means we have a theta. So that's the one that we want. We want to increase one of them, decrease the other one until when we are happy when f of n is equal to theta g of n. So then that's the way. That's to say, okay, then we have the best possible algorithm. What is that case? What does that mean? So because O of f of n it means that your algorithm is going to be the worst case scenario because this is the upper bound. It means in worst case scenario, you are going to reach to this one. It's worse. When you say this one, because it's lower, it means the start from this is the best case scenario, best and worst. It means your algorithm in worst going to be this one. Your algorithm best is going to be this one. If you reach these two together equal to each other, it means that best and worst is similar. So it means you find the algorithm that not do better than this. That's going to be the best in worst and best scenarios. So it means that's going to be our solution. So then we have the best possible algorithm that we have actually. So first of all, if we find this one, for first one, we call it, when we are trying to find decreasing the runtime upper bound. So it's called algorithmic. It means it's going to be this one. And then the second one is called computational complexity. Complexity, G of n, is called a lower bound because it's the lower bound for P. It means in best case scenario, lower bound for the problem P is going to be G of n. So it's called computational complexity G of n. So it's going to be called a lower bound for P. So it means if I want to find the lower bound, which is going to be the best one for our algorithm, it's going to do the best thing is going to happen in the best scenario. So there are two types of lower bounds. It means you're finding the lower bound for your function. So there is one type of lower bound which calls the decision tree lower bound, and there is another one that adversarial argument. So that's going to be LB. So that's two of these things you are going to consider. Just let's give you guys 5-minute break. So, and then I will get back to just talk about two lower bound. Does it make sense? Because you have quiz. I just want to give you guys 5 minutes to just take a break.
Yep.
Okay, sounds good. I will need you just take a break for 5 minutes. So I will keep going on lower bound. Sounds good? Okay. Okay, you guys can hear me, am I right?
Yes,
Okay.
Professor.
So one student asked me again about like extra credit. I just want to mention it again. I will send an announcement about two things. One of them about like the 2 classes that I'm gonna record. And one of them is another one for final exam, another for extra credit. Extra credit is coming from homework 3. So if you want to get any extra credit, you need to submit homework 3. So we are gonna grade homework 3 too. So it's extra credit. So you can solve as much as you want on it. So you can solve 2 or 3 problems, but that's extra credit. And probably because the weight of the homework is higher than the weight of the quiz, it's gonna compensate if you done really good job on quiz. Does it make sense?
I have one question real quick. Is there a due date? Should be
Due
before
date
the
is-
30th?
No, the due date is for Friday. So it's gonna be after exam. Probably when you are studying for exam, you can solve that one. It's not
So-
gonna be too.
So after Friday or Friday, sorry.
It's Friday after the final exam. So if the exam is at 7:15, so you have a time until 12, like
Oh, I see. Thank you.
11:35, something like that. Yeah, sure. So that was one of the student asked me. So in Zoom. So I just want to explain it again. That's it. So let's go back. So I'm just going to write about 2 types of lower bound. So we have 2 types of lower bounds. One of them is decision tree, lower bound. Which we can call it also, we can call it information theoretic. Okay, and the other one is one of the famous one is like adversary argument, which is going to say adversary argument lower bound. So here we say information theoretic lower bound, LB. It means it's going to be lower bound. LB is going to be lower bound. So, but let's talk about decision tree. So let's solve the decision tree. Probably I'm going to teach about decision tree today, and then we are going to talk about like adversary argument on my recording. Let's go back and talk about that. First of all, let's talk about decision trees. Let's have an example. Okay, so let's see. We have M, which is gonna be 1, 2, 3, 4, 5, and 6. So what is that problem? Problem is that determine M by asking a sequence of yes or no question. So probably we can have M from 1 to 6, but we don't know which one is M. So we are trying to ask question to realize, okay, so it's like a guess. I give you a second. I have a number from 1 to 6, and guess which number is it? What you are gonna do, you're gonna just ask question yes or no. So you're asking, okay, is it 2? A second, no. Is it greater than 2? Is it less than that? And then we are trying to find this one, go 1 step down. So what is going to happen actually? So we are gonna have variation of binary search. So what does that mean? Let's start. That's the tree because it's gonna go down. Let's start with depth. So it's okay. This is the depths. So in depths, here I have a depth. I have here number of question. Okay. So let's do this one. A second. Here, start from this. A second. First question in the depths first, which is going to be depths first. The first question, what I'm going to ask, okay, is it less than 3 or greater than 3? That was the first question. Okay, based on this, there's two things. If you go to second question, which is going to be depths 1. If it is less than 3, so probably we can ask, is it less than 2? Less than equal to 2. If it's greater than 3, what we can do is, okay, is it greater than 5? Is it less than 5 or greater than 5? There are two things. Okay, so that's the first thing. This is a step 2. In depths, this is a depths, okay, let's see. This is depths 1, because that one depths 0, and then this is question 2. So I reach here. So go one depth layer down. So here, if it's m less than 2, so there's one thing I can ask. Is it s less than 1? So probably that's one of the questions I can ask. Okay, is it less than 1 or is it 3? So because if it's less than 2 here, so this is gonna be the only thing that I'm gonna get. If it's greater than 2, greater than equal to, the only value is gonna stay, is gonna be 3. So okay, I reached 3 here. So now I'm gonna go one step layer down here too. So m less than less than. So I can say, is it m less than 4? Because we already asked about less than 3. So is it m less than 4? Here, if it's not the case, is it not less than 5? Is it gonna be 6? It means we reach out here to 6. And then we go one layer down. So here, what's going to happen? There are two things. It's gonna be 1 or 2, based on my guess. I know it's gonna be less than equal to 1, so it's gonna be 1 or 2 at this layer. And then here, I know this is gonna be, there's 2 options. This is, if I go down here, so there is 2, oh my gosh. So there is 2 options. Is it 4 or is it 5? There's nothing more. So that's the thing. So you found 1, 2, 3, 4, 5 based on how many layers? Depths 1, 0, depths 1, 2, depths 3, and then you ask 1, 2, 3, and then you go to the layer. Because you ask only what? You ask only 3 questions, and then based on 3 questions, you will find it. So worst case scenario. So it means that a worst case scenario. So because we go only 3 questions, okay, we say worst case number of question is gonna be 3, because you cannot better than that, because that's the minimum. So average, you say average case number of question. How you are going to calculate that? So you know, in the worst, you need to ask 3, but in the best, what's going to happen? So you have 6 number you're trying to find. So the average, you can say, probably I can ask 3 questions 4 times, or 2 questions 2 times. There are 2 options. You can see this one. For example, this 6 and 3 and 6. You ask only 2 questions. And for the next one, which is going to be 3 questions that you ask, you have how many? 1, 2, 3, 4. That's the average. So it's going to be, the average is going to be 8/3, which is going to be 2.66. It means in average, that's a number of questions. But in the worst case scenario, so you're going to ask 3 questions, which is going to be worse than 2.6. So that was one of the way that you can calculate. This is the variation of binary search. That's one way. But let's do another, linear search as a decision tree. This is binary. What do you mean? Why it's binary? Because every time you consider, okay, is it less than 3 or is it greater than 3? There's yes and no question. You just don't consider everything. You just keep one. For example, if the middle one is like 3 or 4, here is only we have this number. If you have one more, like minimum, middle, you find the middle. It's okay, less than that middle or greater than middle. You just binary search. It's going binary. So okay, is it yes or no? But if you do linear search, let's do linear search. What is linear search? Linear search as a decision tree. I'm trying to solve this problem the problem like this one, M, which is the what is the number N, with different decision tree. One was the binary search, we calculate that one. Let's do linear. What do you mean? So, okay, first of all, I ask, is it M equal to 1? You say yes, is it? So that's perfect. Good. So the next time I go, no, if M is equal to 2, and I say yes, so you did it, or no, it's not. So then you can ask, okay, is M equal to 3? If it's yes, it's okay, yes, is it 3? Okay, let's do better. I need all the way go down. So I start here. I say, okay, M equal to 1. Say, okay, yes, this is 1. If it's not, it's like M equal to 2. If it's yes, so we return 2. If it's not, we go 1 layer down. M equal to 3. Also, okay, yes, this is 3. If it's not, I'm gonna go 1 layer down. M equal to 4. So I'm just putting 4. If it's not, I'm gonna ask, is it M equal to 5? That's like a yes, so it's gonna return 5. If it's not, so it's gonna be 6. There's 2 options, like a 5 or 6. So how many questions I ask? 1, 2, 3, 4, 5. So in worst case scenario, so it's like a worst case number of question is 5, because I already asked 5 questions. But the average case is gonna be okay. I asked 1. I asked 2 questions, because here when I go 2 layer, I asked equal 1, and it was, I asked M equal to 2. It means every layer I go down, 1 layer is gonna be considered. Like, let me write average case. So it's gonna be like this. 1 question. If I go 1, 2 question, and then 1, 3 question, because I go to up to 3, 1, 4 question. But for the last one, I ask 5 questions, I get 2 results. It's gonna be 2 of 5. 2 of 5. It's gonna be actually multiple. It's better to put it like this. If that's the case, and then we have 6 numbers that we need to consider, is 20 divided by 6 is 3.33. What is that shows us? As you remember, we check this average case and worst case. We are trying to solve this problem when we get the better result. As you can see, if I do it with binary, in the worst case scenario, I got 3 questions and then 2.66 in average. But if I just keep going with the linear search, it means I do 1 step ahead, I do it again and again. You can see in worst case scenario, I need to ask 5 questions. And in average, it means that in average, I need 3.33. So still both of them, not only average, worst case is for sure. Average is still worse than the worst in the previous one. Because the previous one, the worst case scenario was 3. But here is worse than that, it's 3.33. So that's the way it shows you're trying to solve one problem. What was the problem? So it's okay, let's solve the problem, P. That was the case. It's like find the asymptotic bound. What is the worst case? What is the worst case scenario? And then you're trying to find this one and trying different algorithms. So, okay, this is the best one because this is going to be the best. Worst case scenario and average case scenario is better. So as you can see, one of the way to find an number is a binary search. That is a really, really famous algorithm to do. Probably because as you can do it based on decision tree, as I showed you guys, this is better. Not only in worst case scenario, but also in the average case. That's one of the way to solve a problem. Instead of like, for example, if you want to find a number here, like, let's see, I have a problem. So I have an array. A is going to be 22, 3, 25, 62, 12. Actually, let's do sorted. 25, 30, 62. Let's see. I want to check this algorithm. What I can do, I know it's already sorted. So what I can, instead of going one by one, check the first one, second one. What I can do binary search. Binary search to do what? I want to see if 26 is the number in the array or not. That's what I'm going to do. What I'm going to check is, okay, let's start from the middle one. And they also like, if 26 is greater than middle one, so let's go ahead with this way instead of calculating all the array. Or if it's greater, just don't do this one. That's a binary search that we do. Actually, binary search is the one of the algorithm that you can consider. It's probably useful to do some of the problems. Probably I will explain it in the other class, but you need to learn about binary search. This is one of the algorithms that's really, really important in the future, whatever you want to try, and solving any problems. So I hope it makes sense. Does it make sense? Okay, so anybody has any question? Okay, you guys don't have any questions. So I explain again. Tomorrow we don't have any class. I will post the 2 section on Wednesday, and then I will post the homework 3, and we have an exam on Friday. Anything else need to be clear? I will extend the homework 2 deadline until tomorrow, 8 p.m. And I will send an announcement. Anything need to be explained? Clear? Okay, sounds good. Have a great evening and talk to you guys on Wednesday.
Okay, thank you.
You're welcome. Bye, everyone.
Thank you.
You're welcome. Anybody has any other question, or you are good? You're welcome.